Dear all, good morning. Our next lecture is quadratic forms and positive definite matrices. In this lecture, we are going to discuss quadratic forms and how to write corresponding matrix of quadratic forms for positive definite matrices. When we say a matrix is positive definite, now first, what is the quadratic forms? The definition: let x variable vector be an arbitrary vector in Rn space. A real quadratic form is an homogeneous expansion of the form. Homogeneous expansion of the form. Homogeneous means each term degree is same. A quadratic means the each term degree is 2. The quadratic form Q of x equal to the summation where I varying from 1 to n and j varying from n to 1 to n aij into xi xj. This is the quadratic form in which the total power in each term is 2. In the total term in each term is the degree of each one. So we're expanding. So expanding this q of x equal to I is equal to 1 to n. So if you take I is 1, j varying 1 to n. That means you can write a11 x1 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 that x1 square plus a12 x1 x2 plus and so on a1n x1 xn. Next plus I is 2, j varying from 1 to n a21 x2 x1 plus a22 x2 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 square and so on a2n x x x2 xn plus a3 x1 a31 x3 x1 plus a32 x3 x2 plus and so on. Last a n1 xn x1 a n2 xn x2 plus a nn xn 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 square. So on. Same as a11 x1 square. Now observe here x1 x2, the second one x2 x1, same as x1 x2, the product if you take x1 x2 common, a12 plus a21 x1 x2 plus a22 x2 square plus, now observe here x3 x1, if write here this one a31 if write here a12 a13 x1 x3, that means we get a13 a31 x1 x3 and so on, right? Last ann xn square. By using this matrix multiplication, the definition of matrix multiplication, we will get x transpose ax. This one will get both. Take this equation one x transpose, where x is the vector, a means the matrix. A will get a11 a12 and so on, a1 a21 a22 a2n and so on, an1 an2 plus a. If I'm using this x transpose ax, this is the transformation. A21 a12 a2, this is the one where a12 a21 will now suppose, now set, suppose I'm taking set bij equal to aij plus aji divided by 2. Now the matrix Now here a11 x1 square, a12 plus a21. Okay. That one. Now the matrix I'm setting B equal to Bij. The matrix is Bij is symmetric because symmetric. It says why it's symmetric since B is Bij I'm setting Bij equal to Bij equal to this one. If you write Bj the sum is Bj is Aj and Aij. That means same as Bij equal to Bj. Further Bij plus Bj is equal to Aij plus Aj. Both are same. So summation. Hence the equation one, this one x transpose Ax can be written as can be written as P of x equal to x transpose Bx, where B is a symmetric matrix. Symmetric matrix. Now, from quadratic equation, write a symmetric matrix. Symmetric matrix, and you can write Bij equal to Aij plus Aj divided by 7. For example, n equal to 2. Suppose we are taking only two variables x1, x2. N equal to 2, we have in the quadratic forms only up to x1, x2. That x1 square coefficient a11. It means here b11 equals same as a11, b12 equal to or same b21. Symmetric b12 same as b21. This equal to a12 plus a21 divided by 2, and b22 equal to a22. The one. N equal to similarly for n equal to 3 we can write b11 is same as a11, b12 b and b21 is same and up to 1, and b33 is a33, b13 and b equal to b1 same, b13 b31 equal to we get a13 plus a31 divided by 2 and so on like that. So example you can take, right, and the symmetric matrix B for the quadratic form, form Q of x equal to x1 square plus 3 x1 x2 plus x2 square. This is the one. Or you can compare or write solution. You can compare or you can write directly. Now comparing quadratic form, general quadratic form, we have the x1 square, that's a a11. a11 equal to 2. x1 x2, that means a12 plus a21 equal to 3 and a22 equal to 1. Therefore, for the b11 same as the a11, this is 2, and we are at B symmetric matrix. That means b12 we require b21. b12 b21 is a12 plus a21 by 2. This is 3 by 2, and b22 equal to a22. This is 1. Therefore, symmetric matrix B equal to What is B matrix? B11, 2, B12, 3 by 2, B21, 3 by 2, B22, 1. This is a symmetric matrix. We will take another example. You can write directly. Suppose if it's given quadratic form. Okay, let I give it. Suppose it's given quadratic form. Suppose of x equal to x1 square plus x1 x2 x1 x2 minus 4 x1 x3 plus 6 x2 x3 minus 5 x2 square plus 4 x3 square. Suppose it's given quadratic equation. Now the matrix. For writing this matrix, I am writing here. Observe here. Writing matrix. Now the symmetric matrix. Symmetric matrix B equal to or B whatever symmetric matrix B or denote A or whatever symmetric matrix B equal to here 3 variable. That means you get 3 by 3 matrix. X1 square, x2 square, x3 square. The diagonal elements. X1, x2. That means B12 and B21 divided by 2. So 1, B12. 2 is there, you have to take half of that one. By 2 is 1. Next x1, x3. A13 element or B13 element. Minus 4 is there. That half element is minus 2. Now the same element 1. B12 and B21 is same element. Diagonal element is x2 square. That's a minus 5. Next B23 means x23. x23 is 6. The half one is 6 by 2 is 3. Next B31 same as the B13. That's minus 2. Next B32 same as B23. That's 3. Now B33 means x3 square. That's the 4. This is the matrix. Directly you can write. Need to compare. Directly you can write matrix. This one can write. It's given quadratic form. This is a matrix corresponding to quadratic form. Now suppose if it is complex matrix. Suppose if A is a complex matrix, then the quadratic form is defined as like this one. This is a complex. This is x star means already you know. This x star equal to x conjugate transpose. X transpose Ax. This one. Where x is the arbitrary vector in Cn, that is a complex plane. However, this quadratic form is usually defined for Hermitian matrix. The complex one is defined for Hermitian matrix. Similarly, usually we define that real quadratic form is usually symmetric matrix. This is the Hermitian matrix, complex one. This is called a Hermitian form. Sometimes the quadratic form also called Hermitian form is always real. The quadratic form is always real. Now see some example. This is a quadratic form conjugate vector x star Ax. That x star means x conjugate transpose. This is sometimes called Hermitian form. Form is always real. The form is always real. Suppose take this one. Q of x equal to now x star Ax. X star Ax means x star. Let x equal to suppose we take let x equal to x1 x1 x2. X star Ax means that is x conjugate transpose Ax. X is this one x conjugate transpose. Conjugate means x1 and transpose means row that x1 x2 A 1 plus I 1 minus I and x1 x2. Now multiply this one, the matrix multiply, usual matrix multiply x2 conjugate. If you multiply this one x1 plus 1 plus I x2 1 minus I x1 plus 2x2. Now again multiply this one, will get x1 and x1 conjugate mod x1 will x1 square will get. Next plus 1 plus I x1 conjugate x2 plus 1 minus I x1 x2 x1. Next this one 1 plus I x1 x2 conjugate plus into x2 x2 conjugate mod x2 square. You know this one, mod into z bar equal to mod z square. Now this is equal to this one. The real, this one real. Now what about this one? This term 1 plus I x1 conjugate into x2, 1 minus I x1 into x2 conjugate. Suppose taking okay, x1 equal to some 1 plus ip1 iq1 and x2 equal to p2 plus iq2. When you take this one, we obtain x1 conjugate x2 plus x1 x2 conjugate. Very clear this one. x1 conjugate x2, because this one you can write 1 plus I. You can write one more step. The same as you can write mod x2 x1 square plus 1 1. That means x1 conjugate x2 plus x1 x2 conjugate. If I common plus I into x1 conjugate x2 plus minus x1 x2 conjugate. This same. Okay. x1 conjugate x2 x1 conjugate. If I take I common, x1 conjugate x2 minus x1 x2 conjugate. This one. We obtain x1 conjugate x2 plus x1 conjugate x2 equal to this one p1 x1 conjugate means p1 minus iq1 p2 plus iq2 plus p1 plus iq1 p2 conjugate p2 minus iq2. Simplify this one. So p1, this one will get p1 p2 again here p1 p2. That means we get 2 into p1 p2 minus iq1 p2 here plus iq1 p2. This is cancelled. We will get this one p1 p2 plus q1 q2. This one will get. Similarly, we get x1 conjugate x2 minus x1 x2 conjugate. This will get 5 into p1 q1 q2 minus p2 q1. We will get this one. Now this 2 one we can write. We can write this one. We can write x1 conjugate x2 plus x2 conjugate x1 plus I into x1 conjugate x2 minus x1 x2 conjugate. If you write this 2, if you add this 2 1, you take 2 common, so p1 p2 plus q1 q2. Here 2i and here I is there. I into I square minus p1 q2 minus p2 q1. It's the same thing. This one, if you can this way same as real into 1 plus I into x1 conjugate x2. Both are same. Total term you can write 2 real into 1 plus I into x1 conjugate x2. If any doubt you can check 1 plus I into x1 conjugate into x2, you get the same term. Yeah, therefore q of x. What the q of x is? Mod x1 square. Yes. Now x1 conjugate x2 plus x2 conjugate x1 plus I into this term. This term is the 2 real into real part of 1 plus I into x1 conjugate x2. The total is the real part plus 2 x2 square. The total is real. Hence the quadratic form. Hence form is real. Means that matrix is Hermitian, and that quadratic form is always real. Form always real. The quadratic form always real. Next, positive definite matrices. Now, what is the definition of positive definite matrices? Let A is any matrix, n matrix, suppose a square matrix, whatever n by n matrix, you can suppose you take n by n matrix, square must be. Then the matrix A is said to be positive definite. Positive definite. If the quadratic form x star Ax is always positive, any non-zero vector. X star means the conjugate transpose into A into X vector. X is any vector, positive. And X transpose x star Ax is 0 if and only if x is 0 vector. 0 vector is 0, non-zero vector is must be non-zero. When that x is non-zero, if it is positive, then A is called positive definite matrix. If A is real, then x can be taken as real. If A is real, this x we can take real. This always we take real. Now, this is a positive definite matrices definition. Now, positive definite matrices have following properties. First one, the eigenvalues of positive definite matrices are all real and positive. The eigenvalues of positive definite matrices. Generally, we take to different symmetric matrix. The eigenvalues of symmetric matrix is always real. Not only symmetric matrix, whatever real matrix. See, eigenvalues of positive definite matrices. The eigenvalues of positive definite matrices always real and positive. And this simple. You have to so that this is eigenvalues is positive. Let lambda be an eigenvalue of a corresponding eigen with corresponding eigenvector with x for this one. That is, the definition of eigenvalues x equal to lambda x. Now this one, if you multiply with x transpose x equal to lambda x transpose x. Now you have to take this lambda. What is the lambda? One you can write lambda equal to, because this is a positive definite. Okay. Okay. Let A be positive definite. Definite. Let A be positive definite and lambda be an eigenvalue of A with the corresponding eigenvalue x. If positive definite means this is positive. Then, can I write x transpose x equal to lambda x transpose x. Okay. Lambda equal to what is the x transpose x divided by x transpose x. One. We know x transpose, since whatever this x transpose x is always greater than 0. Already we know this one. And if A is positive definite. If A is positive definite means x transpose x is positive. You can write since A is positive definite. Positive definite. This x transpose x is positive, this is positive. Which we obtain lambda is positive. We obtain lambda is positive. A is positive definite, we get lambda is positive. Now you have to show that this is real. Suppose if A is Hermitian matrix, Hermitian. Well, if is Hermitian matrix, then x star Ax. Just now we see that x star Ax is real, and the Hermitian matrix. What are the eigenvalues of Hermitian matrix? Also real, and lambda is real. This lambda is eigenvalue is real. Therefore, yeah, x transpose x is real, lambda also real. Therefore, if the the quadratic Hermitian form 0 is also positive. This is positive means the Hermitian form also. This is positive because x transpose Ax. Suppose we are taking Ax equal to lambda x. So you are multiply with x star both side. X equal to lambda x star x. Lambda also we can write x star x equal to x star x. This one we can write. This one is real. Suppose we are taking this a positive definite. The Hermitian form must be positive. Then the eigenvalues are real, and positive. The eigenvalues of real and suppose we are taking A is any matrix, we get lambda is positive. Suppose we are taking Hermitian matrix, the quadratic form. If you take Hermitian matrix, then we are getting this form also positive. The eigenvalues of Hermitian matrix is real. Means the eigenvalues are real and positive. That means you can remember that means suppose A is positive definite. Positive definite means if and only eigenvalues are positive. Positive. If eigenvalues is positive, you can say A is positive definite. If A is positive definite, all eigenvalues are positive. Now second property, all the leading minors of A are positive. All the leading minors. Suppose you are taking 2 by 2 matrix. Suppose we can take A11, A12, A21, A22. Suppose you are taking this minor, not a symmetric, whatever any matrix. Leading minors means you take determinant of A11 has to be positive. Next, determinant of 1 by 1 matrix, determinant of 2 by 2 matrix. This is total one. So suppose you are taking A is 3 by 3 matrix. A11, A12, A13, A21, A22, A23, A31, A32, A33. Now you have to take all minors. Now you have to find determinant of A11. Next minor, the second minor, this minor. Now determinant of A11, A12, A21, A22. Next determinant of total one. Now total one means determinant of A. Total determinant. All leading minors. Means all leading minors are positive. At least one leading minor this is not positive. That means it's not a positive definite match. Now some remark. Suppose if A is Hermitian, suppose A is Hermitian, strictly diagonal dominant. Diagonal dominant means the mod of AII. That means diagonal matrix A11 like greater than, except this element, sum of all is more. The Hermitian matrix, suppose this means diagonal element is more than remaining elements. Positive real elements are diagonal with positive real elements. Diagonal elements of the Hermitian matrix are positive real numbers, not negative. It must be positive real elements on the diagonal. Then A is positive determinant. It is applicable only Hermitian matrix. If a Hermitian matrix, if it's diagonal dominant, that we can say it's a positive definite. Or you can go for another method, all leading minors, or you have to check eigenvalues. If all the eigenvalues are positive, it's a positive definite matrix. Next, if x star x greater than or equal to 0, then the matrix A is called semi-positive definite or positive semi-definite. Positive semi-definite, you can say. Semi-positive definite, positive semi-definite. Then x star ax greater than or equal to 0. That means equal also 0. But it's a non-zero vector. If it's 0 vector is 0. That means for this one, semi-positive means at least one eigenvalue is 0. Suppose when you are finding eigenvalues for that matrix, at least one eigenvalue is 0, remaining all are positive. You can say semi-positive definite or positive semi-definite. At least one eigenvalue is 0. Matrix A is called negative definite. If it's negative definite, minus of A is positive definite. All the positive eigenvalues, it's a positive definite. If you get all the negative eigenvalues, you can say that's negative definite. That means all the, yeah, that's same. All the eigenvalues of a negative definite matrix are real and negative. All are negative. If all eigenvalues are negative, then values of A are negative, then A is negative definite. Suppose all eigenvalues are negative, one of the eigenvalue is 0. You can say negative semi-definite. Suppose if at least one eigenvalue is negative and eigenvalue is 0 and remaining are negative, then the matrix is called one eigenvalue is 0 and remaining eigenvalues are negative, then the matrix is called negative semi-definite. Negative semi-definite. Suppose it's not positive definite or positive semi-definite, negative definite or negative semi-definite. That one indefinite, you can say. Indefinite. That means it's not any indefinite. It is not satisfiable all. Above. Or you can say, suppose if a matrix has positive eigenvalues as well as negative eigenvalues. Club of positive and negative. Positive eigenvalues and negative. Then the matrix is called indefinite. Indefinite. The matrix is called indefinite. Suppose we take example. Suppose yeah. Now this is the positive definite or negative. P1, 4. Now we can go for three ways. You can check three ways. First one, say that quadratic form is positive or not. X transpose X. Now method 1. Now you can check of X transpose X. Okay. Let X equal to x1 x2. Now take this real matrix, real vector X transpose X. For the X transpose X transpose means x1 x2 p1 2 4 x1 x2. Now multiply this one. Whenever multiply this one, okay, x1 x2, this one 3x1 plus x2, 2x1 plus 4x2, this is equal to x1 square plus x2 x1 plus x1 x2. That means you can have 3 x1 x2 plus 4 x2 square. The same as you can write this one 3 into x1 plus 1 by 2 x2 square plus divided by 4 x2 square. So now observe here, this all are squaring term. The square term always positive, all x not equal to 0. All non-zero vector. All are non-zero vector, this is positive. Therefore, A is positive definite. Therefore, A is positive definite. This one, first method. Now method 2. Now find eigenvalues. Now find eigenvalues, characters. A minus lambda is equal to 0. That implies we know lambda square s. Case is 1. 1 lambda minus plus determinant. What is the determinant? 12 minus 2 plus 10. Okay. This one you can write 9 minus 2 into lambda minus 2 into lambda minus 4. May I correct? This is 0. What are the eigenvalues of A are 2, lambda equal to 2 comma and they are positive. They are positive. Yeah, we are getting eigenvalues 2 are positive. Yes. A is positive definite. Second method. Third method we can say leading minus. Method leading minus. Leading minus is determinant of element. What is the determinant of 3? If it is minus 3, the determinant is minus 3. Determinant not mod absolute value. Determinant of 3124. Equal to 10. All leading minus are positive. Hence, A is positive definite. Not necessary to verify all the methods. You can go for any method. You have to check its positive definite or okay, you can not necessary. Not necessarily check all methods. All the methods. Go for any one of the method. Check eigenvalues, quadratic form is true or not, or you can go for leading minors. If you go for any one of the method, not all methods. Now go for second example. Suppose take this Hermitian matrix 3 minus 2i, 2i, 4. Now this one you can go for 4 ways. You can check quadratic form or diagonally dominated or not, and eigenvalues minors. The minor is non-zero and this also 12 plus 4i square 4. 12 minus 4 8. That is positive. That all minors are positive. Therefore, it's positive definite. Or you can check diagonal dominated. Now you can see, no, when the diagonal dominant, when the matrix is Hermitian. For another matrix symmetric, it's not applicable since A is Hermitian. And diagonally dominant. Diagonal dominant. What the diagonal? It's greater or equal to mod of, except the diagonal element, remaining sum of remaining elements. Mod of minus 2i. This is what the mod of minus 2i, 2. This is more than 2. And the diagonal element is 4, greater than mod of 2i. It's also true. It's the same. It's a diagonal laminate. This is the region. Diagonal laminate with diagonal element must be positive real numbers. It's positive. It's positive real diagonal elements. Therefore, A is positive definite. Give one of the reason. It's enough. If it's not a diagonally dominant. Now you go for eigenvalues. Finding the eigen. Suppose there 2 is there. So in place of it, here 2 is there. But the 2 greater than it's not greater than minus mod of minus 2i. 2 equal to this, 2 equal to 2. But it's not diagonally dominant. That means this method is not applicable. Go for the finding diagonal elements or leading minus. The leading minus is, now check leading minus are positive or not. If leading minus also not satisfied, go for eigenvalues and eigenvalues. Third example. Now see this one. 1 0 I 0 1 0 I 0 3. Now this one, it's not applicable. Diagonal elements are positive real numbers, but it's not diagonally dominated. A is Hermitian. The matrix A is Hermitian, but not diagonally dominated. Not strictly, but not strictly diagonally dominated. Diagonally dominated. It's not strictly diagonally dominated. That means this method is not applicable. But yeah, this is not possible. It's not applicable. Verifying. Yeah. Not a verify. It's for not positive definite or not. Now find the eigenvalues. Now characteristic of A is mod A minus lambda is equal to 0. Then now that implies 1 minus lambda 0 I 0 1 minus lambda 0 minus I 0 equal to 0. Now we know this one, lambda cube minus s 5 lambda and minus of diagonal elements. The minus of diagonal elements you will get 6, that's 6 lambda minus determinant is 2 equal to 0. Now we go for synthetic method, we will get roots are lambda minus 1 into lambda minus 2 whole square, this one. Therefore, eigenvalues of A are lambda equal to 1, 2, 2 and all are all are positive. All are positive. Hence, A is positive. A is positive definite matrix. In this way, you can check. This one other way you can go for leading minus. First leading minus one is positive. Or second this one is positive. You go for determinant of 3 is 2. All are positive. All leading minus also positive. You can go for any one of the method. No need to check all the methods. Let's see another example. Example. Let A be a real, real square matrix. So that matrix A transpose A as real and positive eigenvalues. This is the problem. Now solution. Yeah. Now you have to go for the real eigenvalues. We know every symmetric matrix has a real. It's enough to show that this is now it's symmetric or not. Now since A transpose A whole transpose equal to A transpose of A transpose equal to A transpose A. That means A transpose A transpose is A transpose A. Therefore, A transpose A is symmetric matrix. Symmetric matrix. Symmetric matrix. Hence, eigenvalues of A are real. What is O? Now you have to show that it's a positive eigenvalues. Hence eigenvalues of A are real. Now X transpose. Now your quadratic form is positive or not. If your quadratic form is positive, the eigenvalues are also positive. Now check X transpose in place of A is A transpose A X equal to X transpose A transpose. This one X transpose, you can write A transpose AX. The same as can I write this one X transpose AX. You can write AX whole transpose into AX. Suppose this one I am taking Y transpose Y. AX transpose X transpose A transpose. Where AX equal to Y. Y. Yeah, Y transpose Y non-zero vector. Since Y transpose Y non-zero for any non-zero vector, for any vector Y not equal to 0, for any non. Therefore, the matrix A transpose A, this is Y transpose Y is positive. This is positive means X transpose A transpose A X. This quadratic equation. Now this one Q of X you can say quadratic equation, quadratic form. And therefore the matrix A transpose A is positive definite and and hence positive definite means all the eigenvalues are values of A transpose A or positive. Positive. So therefore, all the eigenvalues of A transpose A are real and positive. 7. Not only A transpose A, you can go for A transpose. A transpose also real and two eigenvalues. Or you can say this one A is any matrix A transpose and A transpose A always symmetric. Symmetric and positive definite. Symmetric and positive definite. If positive definite means it's always real and positive eigenvalues. Positive eigenvalues means it's positive definite. A transpose and A transpose A always symmetric and positive definite. Now I'm stop here. Now thank you.